I'm Greg Earle from Virginia Tech, and we are actually funded by both NASA and the NSF to do eclipse-related science, and what you see here is the titles of those proposals. Also, our news contact at Virginia Tech is Lindsay Hawk, and I've given her information to make her more accessible to the press, and if there's any follow-up questions. What we show here is, excuse me, all of the agencies that are funding us or helping us in some way are shown here. And I have a feeling this should have advanced.
It should have gone. But
I get 20 seconds per slide. So just to set the context, this has already been established, but the 2017 eclipse is the first to occur in an epoch when we have a lot of assets that we can bring to bear to study it. So 2017 path is in red, and the other paths that are before and after are in the other colors. As Morris just introduced, the ionosphere is sort of the top layer of these. It's the electrically active region in our low Earth, near Earth environment. And above 100 kilometers, that atmospheric density is low, solar radiation is high, and that leads to the formation of this electrically conductive layer. That's what we call the ionosphere, and it happens to be where comm satellites, space, ISS flies, things like that. Now we know from long history that the ionosphere affects radio waves. Marconi's original radio experiment in 1901 effectively bounced a radio transmission off of the ionosphere in his transmission from Cornwall to Newfoundland. This is what I like to call the breathing chart. The ionosphere breathes. In the daytime it inflates, meaning the density becomes higher, the number of particles per cubic centimeter. In the nighttime it exhales. And so that's going on all the time, and our models predict that very nicely. But during the eclipse, we have different things coming up. The conductive ionosphere affects modern systems like GPS, mildly, over-the-horizon radar, AM radio, and amateur ham radio. And so this just shows those different media and how they propagate through or off the ionosphere. So just to recap, two equations: tenuous gas, add sunlight, you get an ionosphere. Take an ionosphere, add radio waves, you get bent radio waves. That's what we want to study. And so in a nutshell, that's what we're trying to do. So as the moon moves in front of the sun and we get an eclipse, the ionospheric conditions change. We get an artificial night in a small area. The ionosphere starts to deflate, and that changes the radio propagation environment. That is our experiment in a nutshell. So what I like to do to visualize this is imagine you have a magnifying glass over a map. You see a distorted image where the magnifying glass is. It's magnified, and outside of that you see normal. The eclipse is going to create a lens like that moves across the country, but it's not optically visible. It's visible in radio waves. That's what we're studying. The conditions in an eclipse are different from normal sunrise and sunset for a variety of reasons. Number one, the time duration. The eclipse moves from west to east instead of east to west. It happens in the middle of the day when the sunlight is intense. Lots and lots of reasons why the eclipse is special. What we're going to do is build 3 field sites in Oregon, Kansas, and South Carolina. And we also happen to get lucky in that the eclipse is going to move right across the path of 2 HF radars that already exist. In addition to that, we're going to bring in GPS data. This shows what a GPS station looks like, and then this map on the lower right shows the coverage of GPS stations all across the country. That data is public domain. We're going to ingest that and try and interpret our measurements in that regard too. The 2 radar systems that I measured in Oregon and that I mentioned in Oregon and Kansas look like this. They're very large. That's a building you see in the middle. And they will be ideally situated to observe the eclipse as it passes overhead, and will operate in a special mode to help us get data. The ham radio community is also active here. We have a contest that is going on nationwide. There are 700,000 hams in the US, and they've all been invited to participate in a contest that will help us get even more data from the links that they make. Once we have all this data, we're going to deploy sophisticated models from Naval Research Lab that we will use to help interpret the data and better understand what's going on in the eclipse. So what will we learn? Well, in gross terms, how sensitive is the ionosphere to changes in solar illumination? And how does the eclipse affect people and man-made systems? Those are the overarching questions that we're trying to answer. So Virginia Tech students will work in teams. They'll analyze data from all these sources, and they'll test the predictions of our computational models to really give us an opportunity to improve those models. That modeling work will involve our collaborators at NRL as well as our own students at Virginia Tech. So to conclude, our experiment is going to assimilate as much data as we can get our hands on, which is much more than has ever been available during any previous eclipse. And this includes all the sub-bullets that I show here, I won't get into. But using these data, we're going to try and answer those two questions. And the participants and collaborators are on my last page here. We have mostly Virginia Tech, but we've got all the hams. We've got Naval Research Laboratory. We have a collaborator at New Jersey Institute of Technology, and they will all be working together to understand this data, run the models, and test them. Thanks.
Thank you.